we were to just, let's go ahead and take this to the next page. It says, what happens to the energy of the molecules? So if the temperature is rising, and we've talked about that, if temperature is rising all of a sudden, and we saw it on that demonstration, that the molecules have more energy and they're more chaotic, and so what's happening is more collisions. So how does the activity of the molecules change as a result? Well, so the molecules expand away from each other. They're trying to, again, more heat. They're expanding away from each other, just like how a balloon would start increasing and getting bigger. So what happens to the balloon? Obviously, we know because the volume starts to change. It increases. That's where you see that the balloon starts getting bigger and bigger. So balloons try to keep at least their pressure constant. So when the temperature does change, the balloons change their volume because they're so stretchy. I mean, and obviously if the temperature, just like we said yesterday, if you walked outside, and we're going to talk about this a little bit later, but if you walked outside on a cold balloon or on a cold day, you saw that the balloon kind of shrunk up a little bit. It's because the molecules, the temperature is changing, temperature is colder, so the molecules are not moving as fast and chaotic. Let's look at the second one. Describe what happens to a gas in a tank if you increase the temperature. Now remember, this is a tank, so what happens to the energy of the molecules? Well, the molecules have more energy and, again, more chaotic, increasing temperature. Remember that. That's important here. How does the activity of the molecules change as a result? The molecules have more collisions, again, building pressure. And we talked about this a couple of days ago, where if you have more collisions, and I'm going to refer back to that Harry Potter cabinet, again, more collisions equals more pressure. So you got to make sure that we understand. And obviously what happens to the tank, the pressure increases and it can cause an explosion. Because if the pressure increases, where are those molecules going to go? There is nowhere for them to go, and eventually, pop, you have a big explosion, okay? Tanks are to keep volume constant, so when temperature does change, the tank pressure kind of, the tanks change in their pressure because they're not stretchy. And that's why you have an explosion if you have too much pressure within that tank. Okay, they're not like a balloon. Balloon, it can expand, but a tank is only one as is a certain size, and once that the pressure maxes out, boom, you have an explosion. All right, very good. Hopefully you all understand that. Go ahead and give me a, let's see, I'm in the mood for dollars, holla. Go ahead and give me the dollars in your chat box if you understand what we just talked about in the brain stretch. Excellent, excellent. All right, so let's go ahead and continue on. So today, obviously, I'm going to start our recording.
Recording started.
So remember that our class sessions are recorded and distributed for learning purposes. Please don't put any personal information or the information of others into the chat box for your protection and the protection of others. I don't know if I said that again or not, but I don't know. All right, here we go. So our schedule for today, again, if you haven't seen the crazy announcement video, I suggest that you take a look at it. It does give you some announcements for our class, and it also gives you announcements for the school. So if you're interested in any clubs, that's where you need to refer to. Well, today is day 12 out of our 45-day quarter. I couldn't believe it. I can't believe it. This is just flying by. It is April 30th. Folks, it's May 1st tomorrow. Crazy. So today we're going to be talking about our gas laws lab. We're going to have this class until about 2:45, and then after that we will then have a support session if you have any questions or anything else by that. Now, if you have any questions about the lab that we're going to be doing today, let's say a chance that you say that you didn't get number 1 or you didn't get number 2 or whatever it may be. Hold off till the end of class and then ask us there, because we have a lot to get through today, and at the end of class, just hey Mrs. Spolda, hey Mrs. Larkin, can I get number 1? That's like the perfect time to ask us, all right? So today we are going to be working on that 3C lab report and obviously getting that extra credit attendance. All right, so Unit 3, gas laws. We've been talking about gas laws. We've been talking about what is made up of gases, and then we've examined all the laws. Remember the 3 major laws that govern these gases, and paying particular attention to 3 things: pressure, temperature, and volume. And obviously we're going to demonstrate that by through our lab today. So let's go ahead and get started. So obviously designing an experiment based on this hypothesis, and we're going to talk about hypothesis, kind of just brainstorm what is the scientific method, and we're going to analyze the data. We're going to understand the relationship between the temperature and volume of gases and how temperature and volume actually are collaborate together. It goes into the same. And obviously, we're going to demonstrate that through our 3C lab report. Now, we will get, hopefully, cross our fingers, we will get an 80% or higher. You should, because we're going to walk you through it step by step. Now, this is quite different than our notes. We're not going to give you the answers like we would with the notes, word for word. We're going to walk you through step by step. So just make sure that you're paying attention as we go through this. Here is our agenda for today. If you have any questions whatsoever, let us know in the chat box. And if not, let's continue. So right now, I'm going to go ahead and put our lab report into the chat box. There you go. I want you to go ahead and open up that lab report, and I want you to give me a green check when you open it up. Now, we understand, no worries here, that if you cannot open it up, your computer doesn't like doing two things at once. I know there can be very temperamental. Just let us know, and you make sure you get pictures or screenshots of the work that we do today in class. So give me a green check either way so I know you're ready to go. We don't want to leave anybody behind. And remember, all instructions in this lab are provided for you step by step throughout the lesson. So it's important that you pay attention and that you are listening. And if you are watching the recording, make sure you click Content, Unit 3, Gas Laws, scroll down, and you will find your 3C lab report. All right, we have 28 green checks, and I have 50 of us in class today. So I need to see a lot more green checks. Alyssa, I need to see a green check from you. Angelo, green check. Dakota, green check. Desiree, green check. Computers can be very temperamental. I don't understand that. It's crazy. Awesome. Very good, everybody. It looks like we got most to everybody. And just to let you know, here is the links right up onto the screen right there, onto the slides. So if you didn't get the links in the chat box, they're right there provided for you. And like always, if you can't get the links, you go to your grades tab, your one-stop shop. All right? Let us begin.
All right, looking good. Can you all hear me? You are so close to the end of school and you are ready for summer. I love it. Hi, Andrea. Awesome. All right, looking good. Okay, perfect. Let me go ahead. We are going to go ahead and work in our FET demo really quickly, just as a quick review. So let me go ahead and share this with you so that if you want to play around with it, you absolutely can. So let me go ahead and put that in the chat box for you. And then I'm going to share this up on the board. All right, go ahead and give me a thumbs up once you can see my screen. Thumbs up once you can see my screen. Oh no, Kayla. Oh, I'm so sorry to hear that. I had a early August birthday, which often meant my birthday was not during school year as well. So I feel that pain, but that also means I'm not in school on my birthday. Well, happy birthday in advance, because that'll be exciting when it does happen. Cool. All right. So what I want you to do is, if you are in the link yourself, just go to Ideal. All right. And then you're going to go ahead and you're going to open it up so that you can see the particles. So there's a little plus sign. Click on that. And then you're going to go ahead and add 200 heavy particles. And you'll see those begin to float around. A lot of July birthdays. Very cool. So you'll see those begin to float around right there. All right. And what we're going to go ahead and do is then we're going to hold the pressure constant but allow volume to change. And that's the second to last option. It says pressure, but volume up, down arrow means volume can change. All right, so let's go ahead and take a look here. What we're going to do is we're going to actually heat this up, and I want you to tell me, what do you observe happening? So if pressure has to stay constant, but volume can change, what do we observe happening? So I'm heating it up, and tell me in the chat box, what did you just see happen? What did you just see happen? You'll be spending your sweet 16 in the house. Oh no, Anissa. So they did speed up for a little bit. Then what happened to the actual container? I can show you another time. Here, let's take a look at this. So we'll keep the pressure constant. And what do you notice happens to the container as I heat it up? I know it's a little bit hard to tell because it's laggy. So the box started about here, and then I began to heat it up. And what happened to it? I can continue to heat it up. What do you see happening to the box? Yes, the box is actually getting bigger. All right. I know it's definitely hard to tell from the lag. So just pay attention to where the box starts and ends once the lag stops. So right now the box is really, really big though, because I was trying to heat it up. So the temperature is much higher. It's at 420 Kelvin here. But if you notice, pressure actually stayed exactly the same. So let's go ahead and actually cool it down and see what happens. So now you can see temperature is decreasing. It's at 290. It's at 230-ish. Keep going. All right, so temperature is at about 211 Kelvin, but pressure is still at 23.4 ATMs, atmospheres. It hasn't changed. So what happened to the box this time? Go ahead, tell me in the chat box. What happened in the box this time? Yes, the box got smaller. Exactly. So you can see as it gets hotter, the box gets bigger. And as it gets colder, the box gets smaller. All right, so go ahead and give me a thumbs up if that's making sense, what you're seeing in the demo here, okay? Because that's going to be related to what we actually, I wanted you to be able to see the molecular, what's going on molecule-wise, but we're going to be able to see what happens big picture-wise today in our lab report. And yes, we're going to be in the 3C lab report. If it's not letting you open it, Erin, just take pictures of the answers for now and give us green checks when you have the pictures ready, or when you've taken a picture of the answer, and then it'll probably open up after class is over and your computer has more short-term memory. Is it not? Or everyone else was able to get it open though, right? Yeah, the hotter, the bigger the box. Exactly, Leslie. That's exactly the pattern. Okay, perfect. All right, so let's go ahead and actually jump into why that's happening though. So this, remember, is related to Charles' law, which says at constant pressure, the temperature of a gas is directly related to volume. And we saw that in the demo, that when the temperature got hotter, the molecules had more energy, which caused them to expand. They wanted to move away from each other because they got more chaotic, and so the container expanded, it got bigger. Now this can only happen in stretchy containers. And what's the main stretchy container that we can use as an example here? What's the main stretchy container? Think back to our brain stretch today. What container is stretchy and can expand when you heat it up? Awesome. I see Jay typing. I see Louie typing. Dakota, Mike, balloons, exactly. Balloons are the example of a stretchy container. Now, this can't happen with tanks because tanks, their pressure won't stay constant. Tanks, their volume will stay constant, and as a result, their pressure changes, which is why they explode when they get too hot. But for balloons, they can actually get stretchy and get bigger, okay? No, we haven't done any of the questions yet. Now, when we decrease temperature, on the other hand, then the opposite happens. The molecules have less energy, meaning that they don't need to be as chaotic. They move closer together, and so the volume of the balloon will decrease. So you can see that here, lower temperature, lower volume, higher temperature, higher volume. Now, our equation for this is that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature, V2T2. And remember that the units for volume can be different. There are many different ways we can measure volume, as long as the initial volume and final volume have the same units. So the units need to match. Temperature, though, is special. Temperature has to be on what's called an absolute scale, and the only absolute scale that we have for temperature is Kelvin. And so an example would be like 8 Kelvin, all right? That's why I was saying Kelvin when we were looking at our temperature in our demo today. All right, go ahead, and this is all review from yesterday. It's literally the same slide. Go ahead and give me a football if all of this makes sense. I just wanted to review it in case anyone was absent yesterday. That way everyone feels confident going into our lab report today. Excellent. All right, let's check for understanding here.
All right, so I'm going to go ahead and give you just about 30 seconds to go ahead and look at these two things. First of all, we're looking at increased temperature, and we're looking at decrease in temperature. What happens when we increase the temperature? There are three things that could happen. And then obviously when we decrease that temperature, what are those three things that happen? So I'm going to go ahead and give your whiteboard tools. 30 seconds is up on the clock. Go ahead and get started. And that is a good point. Mrs. Larkin just put in the chat box that this is, remember that this is a balloon and not a tank, because obviously you're going to get different results if it was a tank. So let's go ahead and look at our answers. Great job, everybody, for participation. I love it. This is what we love to see. So our answers are, when we increase the temperature, okay, and especially in a balloon, we have molecules that have more energy. We talked about that kind of in our brain stretch this afternoon in the beginning of class. Molecules begin to expand away, okay, and obviously that's why when you look at a balloon, it all of a sudden the volume increases, okay, increases because those molecules are expanding away. Obviously, when we look at decreased temperature of a balloon, we know that, and that's again, if we take that balloon outside on a very cold day, we know that the molecules have less energy. They're not moving around as much. They're not colliding. And so the molecules condense together, and condense just means move closer together, less energy. So they're almost trying to get warm themselves. And obviously, when you take that balloon outside on that cold day, you notice that the balloon will kind of shrink. So what happens is the volume decreases. This is number one in your lab report. So I'm going to go ahead and give you 30 seconds up on the clock, and I want you to go ahead and be very careful as you are putting these into your lab report. They are scrambled up a little bit, and so read very carefully as you put them into your lab report. But once you are finished, please give me a green check in your next to your name. I don't know why I want to say chat box, but next to your name. So green checks for number one. 16 seconds up on the clock. For seconds? Awesome. So I have 26 green checks, and I know there should be more of us out there with 54 of us in class, which I love. Go ahead and give me those green checks. If you are not using, if you're not looking at your lab report right now, please make sure you take a picture or a screenshot and then give me a green check. Give me a green check. So I need to see a green check from Angela. Anne-Marie, green check. Brittany, green check. Cody, green check. CJ, green check. Dominic, green check. Asia, green check. Kayla, green check. Mafi, green check. Matthew, green check. Let's get those green checks in. Thank you so much. We don't want to leave anybody behind, especially in our lab reports. Nice job, everybody. All right. Here we go.
Cool. All right, let's go ahead and actually try to apply Charles' equation really quickly. So we're going to talk a lot about balloons today. Your lab includes balloons, so hopefully you're still excited about balloons popping and stuff like that. So here we go. If I place a balloon that has a temperature of 75 degrees Fahrenheit, that's 297 degrees Kelvin, and it contains 550 milliliters of helium in my into my fridge that is 39 degrees Fahrenheit or 277 Kelvin, what would be the balloon's volume after it is fully cooled, and did the balloon get bigger or smaller? Don't hate balloons. Balloons are lots of fun. All right, let's go ahead and annotate our problem, because anytime we do a math problem, remember, math is easy if you know what you're doing, and it helps us to annotate it so that we know what we're doing. Math is fun when you know what you're doing. All right, so Fahrenheit or Kelvin, those are both measurements for what? Volume or temperature? Those are both what? Volume or temperature? Yes, these are units for temperature, and specifically, which one should I be using, the Fahrenheit or the Kelvin? Remember, we talked about how we have to choose which one to use. Yes, we're going to use Kelvin. Anytime we use these gas law equations, we have to use Kelvin. And this is our temperature, but it's specifically the temperature before or after the balloon changes. This is the temperature before or after we change the balloon. Yes, it's before, and so I'm going to mark this as T1, 1 being the before variables, okay? Now, it contains 550 milliliters. Milliliters is the unit for what? Temperature or volume. Milliliters is the unit for temperature or volume. Awesome. I see Chilo in the chat box telling me what it's the units for. Thank you. Yes, this is for volume, and again, same question. Is this before or after? Is it 1 or 2? Type whichever is easier for you. Is it V1, V2, V before, V after? The volume before or after we change it. Yeah, it's actually V1, right? It's the temperature, it's the volume of the balloon, the temperature of the balloon before I stick them in my fridge. Now, once I stick the balloon into my fridge, all right, my fridge has a temperature of about 39 degrees Fahrenheit or 277 degrees, 77 Kelvin. And so that, again, is that a temperature or a volume? This one we should be fast at because we already reviewed Fahrenheit and Kelvin. Definitely a temperature, and specifically which temperature? T1, T2? Yes, Sheila. Yes, Andrea. Yes, Laura. Yep, this one is going to be T2 because this is the temperature after it's changed and put in the fridge. And again, this time we're going to use Kelvin. We want to use Kelvin. Okay, now the temperature, the balloon's volume after it's fully cooled, that's what we're trying to figure out. That's going to be our V2, and that's our question mark. That's what we're trying to figure out. So let's go ahead and start plugging some of these variables in. So over here, what should I plug in for V1? The initial volume of the balloon based on what I annotated. Perfect, yes, 550 milliliters divided by T1, what was the initial temperature of the balloon in Kelvin? Again, make sure you're using the correct units. We can't use Fahrenheit, we have to use Kelvin. Awesome, I see Andrea's got the right number and units. I see Aaron's working. Jay is working. I'm going to turn off my video because it looks like a couple of you are lagging. All right, yep, 297 Kelvin under here. And then we do also know the final temperature of the balloon. And what should the final temperature of the balloon be in Kelvin? 277 Kelvin. Perfect. All right, so let's go ahead and simplify what we can. Can I simplify the left side or the right side right now? Which one has only numbers? Where you can actually do some math. Yeah, we can simplify the left side. So we can do 550 divided by 297. Grab a phone calculator, a computer calculator, or you can Google the word calculator. Any calculator will pop up. And tell me, what do you get when you do 550 divided by 297? Calculator time. Awesome. I see Chilo. I see Andrea. We are doing this measurement, this simplification over here on the left. Perfect. Yes, you should be getting 1.85. You might have been off by a decimal point when you initially typed it, Laura, but it does look like most of you are getting the right number, 1.85. Now, on the right side, we already determined we couldn't yet simplify this because you can't divide a letter by a number. So I'm just going to pull it down as you see it. So divided by 277 still. But I do need to get that variable by itself. So in order to get a letter variable by itself, we need to do the inverse of whatever's next to it. Currently, what's next to it is we're dividing by 277. So what's the inverse or opposite to get rid of that? What's the inverse or opposite of dividing by 277? Awesome. I see Asia's got an answer. I see Cody, Anissa, Andrea, Mike. Yes, we're going to multiply by that same number. So multiply by 277. And that's going to get rid of the 277 on the right side. But whatever I do to one side, I also need to do where? On the other side. Yes, so we're going to also multiply it by 277 on the other side. So now in your calculator, please go ahead and tell me, what is 1.85 times 277? 1.85 times 277. Perfect, perfect, perfect. I'm going to go ahead and I'm going to leave it as whole numbers just because our initial volume was also a whole number. And so I'm going to go ahead and round it to 512 milliliters. Perfect. I love it. So if this is the case, then when we put the balloon in the fridge, mathematically, we expect the balloon to get what? 512 milliliters versus the original 550. Did the balloon get smaller or bigger? Bigger or smaller? Yes, it got smaller, and that again should make sense based on what we understand from Charles's law, where the molecules get colder, they lose energy, and so they condense, they come back together, and so it gets smaller. This right here should be your answer for number 2, 512 milliliters, and the balloon gets smaller. Go ahead, give me green checks when you have number 2 saved. It's multiple choice, easy peasy. You have 20 seconds. Go, go, go. Excellent. I have 55 of you and about 30 answers, so we're still waiting on about, 25 more answers. Perfect. There we go. There's some more. Just waiting on a few more. 10 more answers. Alyssa, And Anthony A, the first one, there's two of you. Let's get CJ, green check, please. Diego, Dominic, Isaiah, Jamie, Joel, Yuhan, Logan, Nathaniel, Sam, and Zion. Green checks, everyone. Oh no. Well, it sounds like it's fair game once you're done with class then. All right, here we go.
All right, so we're, like I said earlier in class today, we're going to talk about that scientific method. And, you know, we actually do this kind of on a daily basis, and we just not really realizing that we're doing the scientific method. But most scientists follow this method when investigating the world around them, when we do experiments, when we do observations. So the first thing, obviously, we make that observation. We ask ourselves a question. We form that hypothesis, which is, you know, trying to answer that question, and we perform the experiment. We gather the information, analyze the data sometimes, and we draw that conclusions. But sometimes that those conclusions can be disproven. That means that the hypothesis was wrong. Then we go back and we change our hypothesis and start that whole process over again. Sometimes they're supported, and then we can communicate those results. So the scientific method is something that we're going to be using throughout our class here. They're going to be using out throughout, you know, pretty much life. We do this all the time that we don't realize that we're doing the scientific method. All right, so let's look at here. We're going to look at steps 1 and 2, where we, again, in our scientific method, we're going to observe and question. So we're going to use our 5 senses and to observe the world around us, or at least we're going to use a couple of our senses watching this video of liquid nitrogen on a balloon. So when you are watching this video of liquid nitrogen, I want you to think of this question. What are you observing? What can we see is happening in the video, okay? And I want you to hold on to that. And when we come back after the video, we're going to go ahead and discuss it. So if I can get, excellent. And the direct link will be in the chat box if this doesn't show up. Alrighty, so let's go ahead and look back, and hopefully you saw this experiment. Now, liquid nitrogen is obviously very cold when it's liquefied, or nitrogen itself is very cold when it is liquefied. So with that being said, when we go back to our whiteboard, what observations can you make about this video? What did you observe? Put it in the chat box. Okay, it shrunk. Good. Okay. Lost volume. Now, I'm going to tell you right now, I am not a good typer. Okay. It shrunk. I saw that. Okay. Anything else? Air inside got cooler. Excellent. What else did you notice? And then it went back to its regular size after it got cooler or warmer. Okay. Good. Good. Warmer. All right, excellent job. These are very good observations, and that's absolutely right. So what we can go back to is that, you know, when we look at this balloon, or when we look at that video, what question can we come up with? Let's turn that observation that we just took and put it into a question. What kind of question can we come up with when we look at these observations and when we looked at this video? Yeah, exactly. What 2 things are we relating today about? Balloons, okay. Yes, we are relating them about balloons, but good, thank you, Trista. Thank you. Temperature and volume, absolutely. So we can say, what's the relationship, and we're going to get real fancy here, relationship between temperature, temp, and volume. Okay, that's a decent question, right? Because that's exactly what we observed here in the video. We know that there has to be a relationship, because when that cold liquid nitrogen fell onto that balloon, the balloon shrunk, and after that liquid nitrogen kind of went away and the balloon started warming up again, it started expanding again. So obviously there's something with that temperature and volume. Very good. So we're going to take that question here and we're going to make it a hypothesis. So when we make it a hypothesis, obviously we observe that the balloon, when exposed to those cold temperatures, will shrink. And we know that our question goes into how does changing temperature affect the volume of the balloons. We need to now make that educated guess and make an if-then statement. So what statement can I make? Well, if the temperature increases, then what will happen to the volume? What can we say that will happen to the volume? If the temperature increases, based on what you saw in the video, remember after the liquid nitrogen, what happened? Tell us in the chat box. It will expand. Good. So that means if it's expanding, what is expanding? What are we talking about today? Look at the question up here. The balloon, good. The balloon is expanding, but let's refer it back to, if we looked right, good. Thank you, Tristan. The volume will increase. Excellent job. The volume will increase. Excellent. So can we say the same thing as opposite? What if the temperature decreases? What can we say then? If the temperature decreases, tell me in the chat box. Excellent, Angelica. Excellent. Very good. The volume will decrease, right? So this would be our hypothesis. So we're saying that if the temperature increases, the volume increases. The balloon expanded again. If the temperature decreases, they poured that cold liquid nitrogen on it, what happened to the balloon? It shrunk up, it decreased. So that would be a hypothesis. And so we're going to take this hypothesis now, and then we would conduct experiments from it. Very nice, everybody. All right.
Perfect. All right. So we have our hypothesis. Both of those things are saying the same thing. It's just what happens if it increases, decreases. We can make a prediction in either direction. So remember that in an experiment, we have two different variables. The independent variable is what we're going to change on purpose at the start of the experiment. Basically, it's the cause and effect of our experiment. The dependent variable, on the other hand, is what we are measuring at the end. It is the effect of the cause and effect in our experiment. Now, these definitions are not the answer to our lab question number 3, so please don't place these as the answers to the lab. These over here are what are going to be the answers. So our hypothesis is if the temperature of a balloon increases, then its size will increase. Now today we're going to actually measure size in diameter because that's related to volume, but just know that when I say size, I mean diameter or volume. Either of those are fine, so those are both ways that we can measure the size of the balloon. And then the reverse, if temperature of a balloon decreases, then its size will decrease. Go ahead and give me a birthday cake if all of that makes sense. Again, today we're going to measure diameter because that's a little bit easier than measuring the volume of a balloon, because a balloon is kind of wonky shaped. Cool. So in that case, what is the independent variable in this experiment? What are we starting with? Take a look at the start of our hypotheses. That's going to help us figure out the independent variables. What are we changing on purpose at the start? Oh, sorry. Yes, we do have polling tools. Let me give you polling tools. I was like, why are there so many letters in the chat box? Hold on. Let me give you A through D. Okay. Yes, thank you. Perfect. Yes, what we are changing on purpose at the start is the temperature of the balloon. You are absolutely correct. So our independent variable is going to be the temperature of the balloon. temperature of the balloon. And that is going to be part 1 of your question number 3 in your lab. I will give you green checks back, and you have 30 seconds to either write that in for question number 3, part 1, the independent variable, or you can also take a picture and give me a green check. Either one works, but make sure you have the answer saved somewhere so you can complete it later. Go, go, go. All right, I have about half of my green checks. Need the other half. Again, you're filling in for the first part of question number 3 in your lab, that the independent variable is the temperature of the balloon. You can copy that word for word. I'm giving you the answer to number 3. That's why you want to be paying attention during class, because I give you all the answers and then we go over all the instructions for the last few questions. You always have an advantage when you come to class and you are working with us. Waiting on Alyssa, Angelo, Anissa, green checks please. CJ, Dakota, and Isaiah, I want to see your green check please. Jade and Kika, Jade and Joel, and just waiting on a few more. Logan, Nathaniel, just want to make sure I don't leave anybody behind who's trying to get this done. I don't want you to feel rushed. Perfect. All right, thanks for letting me know, Dakota. All right, so part 2 then. Let me make sure I give you polling tools this time, because Mrs. Larkin totally had a brain fart just a moment ago. But taking a look here, what then is the dependent variable? What are we trying to measure at the end of our experiment? And we can take a look at the last part of our hypothesis. So take a look at the last part of our hypothesis, and that helps us figure out our dependent variable. What are we measuring at the end? What's the effect or the result we're looking for? Excellent. I have 3 answers so far. Thank you, Andrea. Thank you, Rosie's on top of it. I see Gabby's got an answer for me. There they are. All those answers coming in. Perfect, perfect, perfect. Get your answers in there. What is the dependent variable, what we're measuring at the end? Please note, again, there are a couple different answers that we would accept, all right? There are 3 different options here that I would accept, but there's only one of them that shows up on here just to make it a little bit more confusing to you, you know? All right, looking good. Let me go ahead and publish those up on the board for you. All right, looks like most of us are saying letter B, and letter B is correct. The diameter of the balloon. I would have also accepted the size of the balloon or the volume of the balloon, but obviously those weren't options in your polling, all right? So what I want you to remember is that all of those are kind of talking about the same exact thing. So I know if you're like, but Miss Larkin, you said that we're talking about volume, you said we're talking about size. Well, remember that the diameter of a balloon is related to the volume of a balloon. So as a balloon gets larger around its fattest part, that also means its volume is getting bigger. It's just that volume is really hard to measure on a weird shape like a balloon. Go ahead and give me a music note if you feel comfortable with that. Again, the answer for dependent variable could be the diameter, size, or volume. So diameter, you could also say size or volume of the balloon. Okay, just choose one of them though. You don't have to type all of that. Perfect. All right, this is number 3, part 2. So that's our dependent variable. Give me green checks when you have that filled out. You have 30 seconds to get that done or take a picture. Go, go, go. All right, I have most of my green checks, still waiting on just a few more. Thank you. Let's start at the bottom of our list. Let's get Zion, Tristan, green checks, please, and Nathaniel. Thank you, Leslie. I see yours. Let's get Logan, Louie, Mafi, Matthew, waiting on Joel, Cody, CJ, looking good, Dakota, Dominic, awesome, thank you. Okay, no worries, Yuhan. You do not need to put what's in parentheses. I'm just saying that if you put any of those 3, I would give you credit. So if you want to put diameter, you want to put size, you want to put volume, all of those things are synonymous in terms of how we're conducting our experiment today. Perfect. All right, let's keep on going. Thank you, everyone. All right, so for this lab, you do need to be able to calculate averages. Okay, so I do show you a specific example in today's lab. I show you exactly how to do it. Sorry, this should be questions 4 through 6. All right, in the instructional video today. But I am going to practice a quick example with you just in case you're not familiar with averages. So an average, remember, is just a single number that kind of represents a list of numbers. And you could also call it the mean. How many of you have heard of averages before? Go ahead and give me a star. If you feel like you're familiar with them, you feel like you could probably calculate one, go ahead and give me a star. Awesome. All right, so the equation is just you take the sum of all the terms and then you divide it by how many of the terms that there are. So let's go ahead and take a look at an example problem. So I took the actual, there's a hidden question 7? Sorry, what did you say? Oh no, there's not a hidden question, sorry. I accidentally wrote that it was questions 5 through 7, but it's actually questions 4 through 6. So what is the average temperature in Los Angeles over the next 6 days? I actually took all the temperatures. So let's go ahead and first off, we need to count how many terms there are. So how many numbers do you actually see here? Not what are the numbers, but how many of them do you see? Yeah, there are 6 numbers. So that's what we mean by the count of terms. So that's what's going to go on the bottom here. Now for the sum of the terms, we're just going to put all those numbers and add them up together. So we're going to take 78 plus, let's see here, 78 plus 79 plus 78 plus 83 plus 87 plus 92. And then we're going to divide it by the count, which again, there were 6 of those terms. So first off, go ahead, simplify the top for me. Add up all those numbers and tell me, what do you get? Use your calculator. What do you get on the top? 9,000 degrees Fahrenheit. Are you sure you don't want over 9,000 degrees Fahrenheit? Yes, Andrea, I see your numbers there. I see Asia, you've got it. Yes, it should be 497 on the top. Now, 497 is just the total. It's definitely not the average because that would be a horrible average temperature over the next 6 days. So what we need to do is we need to divide it by the actual number of days, which is divide that number by 6. So take 497 divided by 6 and tell me what is the average. And the average should be representative, meaning close to most of our numbers. Yes, perfect. You should be getting 82.8. So yes, 82.8 degrees Fahrenheit. That would be the average. And you can see how this average is really close to all these numbers. It is representative of these numbers. Go ahead and give me a sun if you feel good about that. Sun if you feel good about that. I do not feel good about May 6th, though. I'm going to tell you that right now. The day after is even hotter. I chose not to include that on our average. Perfect. All right, so here we go. This will be a video lab just because of the issue with Adobe Flash. So you do need to watch the recording to get the data. It's only a 10-minute video, so it's really fast, and all the data is in the recording. All right, so one more time. Hold on, one more time. The data's in the video, the data's in the video, the data's in the video. So if you email me, I'm going to send you a picture of the slide where it says the data's in the video. All right. So you will be collecting some data. You'll see that in question number 4. You have these 2 tables. So that's what you'll be filling in for question number 4. All the instructions are in the instructional video. All the data is in the video. Cody, I will cry if you email me and ask me where the data is. All right. Make sure you go at your own pace. That's why we record it. That way you are able to kind of go at your own pace. You don't have to feel rushed. Pause if you need to, rewind if you need to, but go at your own pace. All right, so here's the direct link. That will also be posted in today's recording. So if for some reason you lose the link, it will be in today's recording, but I'm sending you the link right now. So that's how you do questions number 4 through 6. Go ahead, give me a green check if you feel like you understand what to do. Red X's if you're confused. Hopefully you've already done lab number 1, so this is familiar with you. This process is familiar. We do the first half of questions in class. The second half, I give you a video so you can go at your own pace. The data's not in the lab. The data's in the video. Hello students, at this point you should have already completed questions 1 through 3 of the lab report. So now we're going to go ahead and work on gathering the data and answering the last few questions here. So what we're going to do is I will be giving you all of the data in this video. So please make sure that you watch the video in order to get the data. Let me show you how we get all of the data points and then I will go ahead and give you the rest of the data. Okay, so let's go ahead and take a look here. So first off, the thing that you need to know is you first need to figure out what the room temperature is. And the room temperature is going to be the same for the entire trials 1 through 6 under room temperature. So you can see right here that this room temperature is 19.4. And so that's what you're going to be wanting to put into your lab report for question number 4. Is that right here, room temperature for number 1, 2, 3, 4, 5, and 6 should all be 19.4. So again, taking a look here, all of these room temperatures as demonstrated by the purple line should be identical. So once you have that, we're going to go ahead and actually do our balloon here. Oh, sorry, let's actually measure the temperature of the water here. So for the water, we're going to go ahead and drop this thermometer in. And for the water temperature for trials 1, 2, and 3, which is the heated balloon, those ones should all be the same, which is going to be 50 degrees. So taking a look here, at this point, you should be able to fill in 50, 50, 50, all for this one right here. Oops, sorry, I got rid of something. There you go, 50, 50, 50, all in the red boxes here. Cool. So we have the temperature of that. We're going to go ahead, grab the balloon and blow it up. Once we have that blown up, we're going to go ahead and drop it into our calipers here in order to measure how big it is at room temperature at this 19.4 degrees. And this is our balloon number 1, our first trial. All right, so taking a look here, this is going to be, it looks like it's 15 point. It's, let's see here, about 4 dashes past. So our first measurement right here should be 15.4. So let me go ahead and fill this in. So again, you should already have room temperatures completely filled in. You should already have water temperature for the hot balloon filled in, but now the diameter at room temperature is going to be 15.4. Okay, so now what we're going to go ahead and do is we're going to go ahead and drop this into our tank, and we're going to put the lid on, and we're going to go ahead and press start and wait for 4 minutes. While I'm doing that, I'm going to go ahead and actually set up the cold balloon as well. So I'm going to grab this balloon, blow it up. Again, room temperature, we should already know. You should have already filled that out as 19.4. I do need to take a temperature of the cold water. So let me grab the thermometer and do that. Put the balloon in the calipers while we wait. And it looks like it's about 5 degrees. So water temperature for all the cold boxes, 4, 5, and 6, should be 5 degrees. So those 3 should be the same as you see right here demonstrated by the blue line. Okay, so coming back over here, I'm going to go ahead and measure my first, my trial number 4, which is my first of the cold trials. And it looks like it is a measurement of 13.9. So 13.9 because it's 9 little dashes past the big 13 number. So let me go ahead and zoom back out of that, drop it into our tank. Let me take out the thermometer first. Here we go. And put the lid on and set a timer for 4 minutes. And let that go. Now, I'm not going to show you all of the other trials. I will just be giving you the data for all of the other trials, but I am going to show you what the final measurements for the balloons are and how I measure that for the trial 1, which was the first one for the hot balloon, and trial 4, which is the first one for the cold balloon. So once that's finished doing that, I'll go ahead and I will fast forward through the time here, and then we'll go ahead and measure that together. And then for the remaining trials 2 and 3, 4, 5, and 6, I'll just be giving you the data for those diameters. Again, you should have already filled out all of the temperatures. So let's go ahead and wait for that to finish. Okay, so at this point we have completed the hot balloon here. So I'm going to go ahead, take off the lid of this, and drop the balloon back into the calipers to see the final diameter after heating. Zooming into that, that looks like it is 15.9. So over here, diameter after heating, I'm going to go ahead and put 15.9. Again, room temperature should be filled out for all of these. Water temperature should have been 50 here for all 3 of these, and 5 for all 3 of the cold ones. I'm going to go ahead and move back over now to the cold one, which should be done in about 20 seconds. You can see that it's definitely kind of getting wrinkly, which probably shows you what's happening to its shape. The warm one, it looks like it got bigger, which makes sense based on what we talked about in class. So now we're going to see what's happening to the cold one. All right, so popping the lid off of the cold one, I'm going to go ahead and drop this one now into the calipers to measure this one. Jumping like that, zooming in, and that one looks like it is now 13.6. So it started out at 13.9, now it's down to a diameter of 13.6, showing that it's smaller, which should make sense. And again, we should have everything filled out in the room temperature column, the water temperature column. All that's left are trials 2, 3, 5, and 6 for the diameters before and after. And this data I'm not going to actually show you in the lab. I'm just going to go ahead and give this data to you. So the data for these last 2 measurements are that the heated balloon number 2 started at 13.8 and went up to 14.4. The third one started at 14.2 and went up to 14.7. For the cooled balloon, that 5th balloon, the second of the cold ones, it started at 15.4, went down to 15.2, and then the last one, 16.3, went down to 16.1. Okay, so that's all the data that you should fill out for number 4. Now, for question number 5 asks you to calculate the averages, which is something that we discussed in class, how to find averages. So remember, in order to do this, what we do is we're going to add up all the numbers in a column and then divide it by the count of the numbers, which in this case, there are 3 of each type. So what you're going to do is to find the average diameter of the balloons at room temperature, take the 3 from the room temperature boxes, add those together to get the sum, and then divide by 3 to get the average. So first add them, then divide by 3. Same thing then, do the diameter after heating, take those 3 numbers, add them all up, and then once you have the sum, divide by 3, and that's your average. All of your averages should be around our numbers, so around 15 something. If you find that your answer is around 40 something, then you did not divide by 3, so make sure you divide by 3. Then do the same exact thing with the green balloons, so take the 3 diameters at room temperature, sum them up, and then divide by 3, divide that sum by 3, again should be around 15-ish, and same thing with your diameter after cooling. This should say after cooling. Is going to be add those 3 numbers up, divide by 3. And again, what we should see is our averages should still reflect this, where at room temperature to heating, the heating average should get bigger, and then for cooled balloons, the diameter after cooling should get smaller. Okay, once you've done that, you'll be able to fill out your conclusion. So it says if the temperature of balloon increases, then its size will increase. First, fill out your data. So what was the actual measurement of the room temperature? Remember, that was 19.4 when we saw this, right? So taking a look up here. Our room temperature is 19.4 degrees. They started with an average diameter of, this is the average you just calculated up here for letter A. So fill in that average right there. And then they were placed in a warm environment with a temperature of, remember that the temperature of this hot area was 50 degrees. And then they ended with an actual diameter of blank centimeters, which again is the average you should have calculated here. And then this proves that balloons in a warm environment, do they increase or decrease in size? So if this final 5B measurement is bigger, they increase in size, which would support our data. If this 5B measurement is smaller, then they decrease in size, which disproves our hypothesis. Then do the same exact thing with the cold balloons. So what was the measurement of room temperature was 19.5. The actual calculation from letter C of their average diameter at room temperature. Placed in a cold environment at 5 degrees. Remember, the cold one was 5 degrees. And then the calculation from 5D, their average diameter after cooling, which you should have calculated up there. And again, this time, if the temperature decreases, size will decrease. What you should hopefully see is that this second one is smaller, in which case the balloons did decrease in volume, which supports our data. If you see that this number is bigger, though, then that means it increased, and that disproves our data. And then go ahead and make sure you submit your quiz, and you are all set. Thanks, and have a great day, everyone. Well, I'm glad that you're beginning to understand math regardless of what class it's in, because that's going to help you in every class, right? No problem, Anthony. We can go back to number 2 and number 1 in just a moment, Yuhan. All right? Perfect. All right, everyone. So, Mrs. Bulvada, do you mind? I'm just going to wrap up really fast. We talked about how... Thank you. We talked how to design an experiment, make a hypothesis, analyze the data. We talked about how temperature and volume are related. And again, you should definitely get an 80% or higher because I'm giving you the data in the video. All right. So really quick on the board, how are we feeling about today? About how temperature and volume of gases are related when they're in a balloon, which keeps constant pressure because it's stretchy. Perfect. All right. I'm loving all the confidence. If you're ever confused, definitely you can stay after class or you can email us and we can always set up another time to do one-on-one tutoring. We're happy to help. We have a lot of time on our hands now that we're on our weird temporary schedule. Right? All right, so make sure you complete the 3C lab. It is due today at 4, but obviously we give you like a 48-hour grace period before we enter zeros. You can even do it after we enter zeros, but obviously the zeros look scary until you get it done. So make sure just do it correctly. That's what we care about more. It's more annoying for us to see a badly done lab report than for you to not have done it yet. All right, so just do it correctly and get it in once you've done it correctly. Cool. All right, I'm going to go ahead and stop our recording in just a moment. If you're watching the recording and you weren't in live class, you can still get attendance by completing the alternative attendance check by tomorrow at 4 p.m. So for anyone who's not in live class, you can still get attendance for today.